Alright, so let's do question 8 of the tutorial. And in this we're asked to use an appropriate Maxwell equation or Maxwell relation to derive an expression for the change of entropy with volume, or the isothermal change of entropy with volume for perfect gases and for van der Waals gases, and then just give some, or to give some especially we'll just basically talk about that. Right, so we first have to start with giving the appropriate Maxwell relation, and the appropriate Maxwell relation essentially is, we have to look to our table, and it is one where we can relate this to pressure. So it is pressure to temperature at constant volume. So in other words, we're given the equations of states in terms of pressure, and so in other words we have something that we can derive or take the derivative of pressure to temperature and then equate it to the entropy change. Okay, so we will basically just take both of these to that. So for A, if we want to calculate ds dv, so we're just going to plug it into this equation now. So dp dt then means we take d dt of what is P for the ideal gas. It's RT over Vm, all at constant volume. And then that can be rewritten, so I'll write this out very nicely and slowly. Vm partial t to partial t. So you see that just becomes 1. So we're left with R over Vm. Okay, so that's for the perfect gas. And then for B, for the van der Waals gas, we again have the S dV isothermally is equal to dP dt at constant volume, which is equal to d dt of, oh no, I've forgotten what it is, RT over Vm minus B minus A over Vm squared. I have to double check myself. Yeah. Right, that's a constant volume. So let's take out all constants. Okay, well, we first can rewrite it as two terms. In other words, we have RT. We have RT times with, we have R, we actually have R over Vm minus B, and we then left with dt over dt minus A over Vm d over dt. So that's just a 1, a number 1, all at constant volume. Right, and this of course is just 0, so the derivative of 1 is just 0, and that's just 1. So we're just left with this R over Vm minus B. Okay, so just to summarize, the S dV T for the van der Waals gas is equal to R over Vm minus B, and ds dV T for perfect gas is equal to R over Vm. So nearly the same, there's just a difference in terms of that B term. And I'm actually going to cut that. Just down here, so that we can talk about that here. Okay, so the next part of the question asks us which one of these two is larger. So the way I want to look at that, so R is a constant, Vm is a constant, right? You agree about that, and B is a constant. So let's make them just numbers, right? So let's say R is equal to, well, R is 8 point whatever, so let's make R 8. Let's make Vm 1 and let's make B equal to 0.1. Let's actually make it 0.5 so that you can nicely see it. So in other words, if we plug in that, then for the van der Waals gas, let's do it in different colors. For the van der Waals gas, then it is equal to 8 over 0.5 is equal to 16. And for the perfect, it will be equal to 8 over 1, which is just equal to 8. Right, so in other words, you can see the van der Waals gas is larger. So as we just can quickly check. So in other words, that B factor, because B is positive, B will always be positive, and B indicates the repulsive forces in the van der Waals gas, right? So the positive repulsive forces in the van der Waals gas will indicate that it is the entropy change with volume, it will be larger in the van der Waals gas. And that actually makes a lot of sense, because we will expect with a change in volume for a van der Waals gas, then with B being what it is, meaning the repulsive forces between molecules or atoms or whatever in a van der Waals gas, to be more disorderly than what a perfect gas would be. So if we want to put it as a perfect gas only has the normal disorder, in other words, the gas molecules being disorderly. But in a van der Waals gas, we have the normal disorder of the gas molecules plus the fact that this B term, this B term in this equation up here, which then adds to the fact that they're repelling each other, adding to the disorder of the expansion. So in other words, making it more chaotic, making it more disorderly. So we expect with an expansion that the entropy will increase, because that's what we're looking at here. We're looking at how the entropy is changing with volume. So in other words, how entropy changes with expansion, with volume change. So if you want to plot it, essentially what we're doing here is we're seeing something like, so for a perfect gas, we're seeing maybe something like that. And then for a van der Waals gas is that. So this is the perfect. So of course, not how it looks like at all in any case, whatever, but just to get the idea going, you understand? So it's more disorderly, there's more disorder happening here. It's kind of the idea that it's trying to get across, and it's because of that B term that this happens. Okay, so that's how you need to interpret these kinds of equations. And it's just a nice way to show that you can sort of do these things with Maxwell relations. And you can of course do it with any equation of state and anything that you want to relate. So I mean, you can relate the entropy, we could have related to the volume, we could have related to temperature, any of the Maxwell relations that you want.